So far we have seen various normal forms like first normal form, second, third, BCNF. So the important property of BCNF is if your table is in that BCNF, so all the anomalies can be eliminated. And second normal form is not important, it's only historical interest. Now the question is what to do if your table is not in desired normal form, like say BCNF, what to do? We have to do decomposition. To understand decomposition, I take one real world example. So there is a company, in that company employees are there and their names we have, and every employee has exactly one car, and every car name decides the parking area. That means whenever nano car goes to parking area D, then another nano car also goes to parking area D. So this is not functional dependency. Yes, it is functional dependency. That means car name decides parking area can be written as car name determines parking area. Similarly, we have one more dependency, that is employee ID determines employee name, because employee ID is the unique identification number. Since every employee has only one car, then see here, can I say like this? If employee ID 1 has nano car, another employee ID 1, since he is the same person, will have same car name nano. That means whenever employee ID is repeated, car name has to be repeated, because every employee has exactly one car. Then employee ID determines car name. Let me write it. Now automatically employee ID determines parking area because of the transitive property. EID to CNAME, CNAME to park area, then employee ID determines parking area. These are the functional dependencies this table contains. Somehow we can explain DBMS that, my dear DBMS, please maintain these rules. For that we have to write constraints. Yes, we can write it. So leave that part. Now the question is this table is in BCNF or not? We will see. Let's list out the rules. Employee ID determines employee name, and car name determines parking area, and employee ID determines car name. So I think here employee ID is the key attribute. The reason it is determining employee name and car name, since car name determines parking area, so employee ID determines parking area. So employee ID is the candidate key. No other candidate key is possible. The reason, so employee ID is essential. You see, no one is catching employee ID. So that's why there is no alternative for employee ID. So this is the only one candidate key, and we have enough experience how to find out candidate keys. Let me go fast. So employee ID is one of the candidate key and only one candidate key. Now we'll check whether this table is in BCNF or not. Is it in BCNF? So first employee ID. This is super key. Yes. So this rule is satisfied BCNF. Now car name determines parking area. Car name, is it super key? No, it's a violation. So here employee ID is super key. So it satisfies BCNF condition. So this violates BCNF condition. We'll see whether this set of rules are at least in 3NF. So this is the only rule which violated BCNF, right? Check only this rule for 3NF condition. Left side is not super key, at least right side prime attribute. So how to know prime attributes? Employee ID is prime attribute, right? Other things are employee name, so parking area, and car name are non-prime attributes. Parking area is non-prime attribute, so it is not in 3NF. Left side is not super key, right side is not prime attribute, that is 3NF violation. So your table is in actually second normal form. I know that, that's why I'm telling it is second normal form. You should check it. So partial dependency, we have to check for the partial dependency, but there is no partial dependency. Let's try that. So these two don't touch because already left side is super key, then automatically your these two rules satisfy BCNF condition, 3NF condition. Whenever any rule satisfies 3NF condition, automatically that satisfies lower normal form condition also, second normal form also. That's why this is the only thing we should check. Car name determines parking area. So is it partial dependency? What is partial dependency? Left side should be part of the candidate key, but car name is not part of the candidate key, correct? So that's why this is not partial dependency. So this is not a second normal form violation. Finally your table is in second normal form. Of course you know how to check it. Now sir, how to convert this to desired normal form? I want BCNF. Why you want BCNF? Whenever your table is in BCNF, so you can avoid the anomalies. That is what our goal, right? So what is the problem? I mean, why you are facing anomalies, we will see closely. So let's see some data. There are three people, 1, 2, 3, and third person has, let's say, BMW car. and it goes to parking area B. Now employee name is, let's say, Raju, and 2 is Rani, 3 is Rakesh. So we know that nano car should go to parking area D, correct? Now if there are 100 employees and every employee has nano car, then you will be writing nano D unnecessarily so many times. Then you get updation anomaly. What is updation anomaly? Suddenly, so the company realized that nano cars should go to parking area E, not D. Then they have to update it like this. Nano means E. But in everywhere they have to update. If they miss it, they get updation anomaly. We know that. Second one, insertion anomaly. I will show insertion anomaly. So some XYZ car, let's say, came into the market newly, let's say XYZ, and this company decided that XYZ car goes to, let's say, parking area A. Then to remember that in the database, they will write one entry like this, XYZ A. Then only other people cannot do the mistake, right? From now onwards, any new person comes with XYZ, then he will definitely write XYZ A. Otherwise, so that dependency will be violated. Your DBMS will take care of that. That's why, first of all, whenever new data comes to our consideration, we have to write the data XYZ and A. But there is no employee at this moment who is owning that car. Then what to do? We have to write null, but employee ID may be primary key, then we cannot write. So this is insertion anomaly. So what I want to say is, so this functional dependency, car name determines parking area, which is actually transitive dependency, which is nothing but a error of 3NF. This is causing a problem. Because of this, so you are facing the problem, insertion anomaly, updation anomaly. See, so if there are 100 such cars XYZ, we have to repeat it. So finally what I want to say is, these functional dependencies will decide whether your table is in a proper way or not. So is it natural association or not? Keeping employee ID, employee name, car name, parking area, is it the right association or not, will be decided by this kind of functional dependencies. So that's why there is a close connection between your functional dependencies, which are errors of BCNF or 3NF, and anomalies and redundancy. That's why, so what we do is, somehow to solve this problem, we'll give that car to employee ID 1 Raju. Okay, so let's say car name is XYZ, it is going to parking area A. Now again you see the deletion anomaly. Suddenly, let's say Raju want to leave the company, then he will take that car with him, correct? Because you are deleting the tuple, then you lose this association. Because only Raju is having that XYZ car, then if you delete this tuple, then you lose association that XYZ is a car which has to go to parking area A, correct? For that, again the same problem, we have to write XYZ A, but we should only delete this employee information. That's why finally this car name determines parking area is not a natural association. That should not be in this table. So what to do? We have to split the table into parts, right? That's what I want to convey finally. So this table should be divided into some parts, so that division should be natural association. Let's see how to divide this table into two parts. So the natural association is, take employee ID and employee name in one, okay, and car name. This is one table. Second decomposition is, otherwise second table is car name and parking area. Keep car name and parking area in one table, and employee IDs and their corresponding car names in one table, so that you don't get redundancy. Example, there is one nano car, so we write nano should go to parking area E, XYZ car should go to parking area A, in that way. So no updation anomaly, because one information is repeated only one time, right? Second one, no insertion anomaly, right? Example, you want to write employee information, we can write here. If you want to write car information, we can write here. So you don't require to write null values and all. That's it. So this is called decomposition. But if you have thousands of columns and you don't know what is the association, like you don't know what attributes are right attributes for one table, then decomposition will become difficult. So when there are thousands of columns, how to automatically decompose your table such a way that they form a natural association. We will see that. Now we'll see how to decompose a table into BCNF. So one example is given. So we have a mechanical procedure that is called hierarchical decomposition technique. Using that, we are going to divide your table such a way that that will be converted to BCNF. That is the only solution we have, right? So we'll see that how to decompose that table. First of all, if it is already in BCNF, nothing to do. Why to decompose? If your table is not in BCNF, then we have to decompose. First of all, identify your table is in BCNF or not. For that, we have to see BCNF condition. Left side should be super key. So in this table, A is actually candidate key. So A is a super key. A is a super key. So A closer is ABCD. No problem. B is not a super key and C is not a super key. That's why these two are BCNF errors. Whenever you want to decompose this table into BCNF, then we have to take every error of BCNF and we have to create a separate table. So did you remember in the previous problem, car name determines parking area was the problem, right? That was creating unnecessary redundancies, everything, insertion anomaly, deletion anomaly. So what we did you remember? So we have created a separate table for that. In the same way here also, so we are creating separate table for B to C. That is the first step. Take your old table ABCD. This was our old table. Now I am splitting it into two parts. I will tell you how to split. First take this error BC, create a table. Right? Now you remove B comma C from ABCD. That means here you write remaining attributes A and D. Correct? But the problem is if you separate like this, what happens? There is no common attribute. If you don't have common attribute, then we can't relate them, right? So that's why one common attribute is compulsory. So we can either keep B, otherwise C. So we keep B. I will tell you the reason for that. Generally, so B will be kept where the rule is B to C. Whenever you create B to C rule as a table, B should go as common attribute. We'll see the reason later. So let me do that first. Now we do the projection. That means, so these are the rules which are maintained by your DBMS or which you want to, get maintained by DBMS, right? A to B, B to C, C to D. These three rules are very important. So when you divide the table into two parts, again these rules has to be maintained somewhere, either in this table or this table. So example, you have attributes A comma B in this table, right? Then it is better to maintain that rule here, A to B. This is called in theory projection. So let me project the rules. So B to C here, C to D. So C to D is not projectable because we don't have CD in this table and this table. But in this model, we have to project all indirect rules also. I will tell you the reason. Example, A to B, B to C and C to D. Then B to C, C to D. Then there is a indirect rule called B to D because of transitive property that has to be projected. Why? B to D is maintained in this table, right? It is there. But here you have after all A to B, B to C. Using that, can you get B closer as D? Apply B closer here. If you maintain only these two rules in your decomposed tables, then B closer is what? B determines B, B determines C. Anything else? No. But in your old table, we were maintaining B to D. That's why here also we have to maintain B to D. That is the concept. So simply I can say that all indirect rules also we have to explore and we have to project them. So one indirect rule is B to D that we have to write. Fine. Now similarly, sir, A to B, B to C, C to D, then A to D. So A to D should I write? It's up to you. You can write, otherwise you can leave. Sir, why I can leave? A to B, B to D, if you maintain, automatically A to D will be maintained. So that is not required. So only essential things it is better to write. Now anything else? So let's try that. A to B, B to C, then A to C, but we don't have C. Correct? Now these are the only rules. So A to D is optional because that is obvious, right? When you have A to B, B to D, A to D automatically will be maintained. Now this is called projection. Once you project the rules, then again we have to see whether this table is in BCNF or not, this table is in BCNF or not. Here I would like to tell one point. Whenever a table contains exactly two attributes, then automatically that will be in BCNF. We'll see that part. Why a table with two attributes automatically in BCNF? Case number 1. Let me divide this problem into cases. Whenever you have two attributes, only these are the possible rules. One is B to C, that's it. That means one attribute determines another attribute. If this is the only rule if you have, then B will become super key. So this is in BCNF. Try to understand. So this is case number 1. In case number 1, so in your BC table there is only one rule, that is B to C, then automatically that is in BCNF. Second case, what if you have C to B? Same concept, right? So C will become super key, then left side when you have super key, that is in BCNF. Sir, what if I have two rules like this, B to C, C to B? Then automatically B will become super key because B is determining C. There are only two attributes, B is determining all. Similarly, C is also determining all. So B will become super key, C will become super key. So in this case also, so your table is in BCNF. There are only three cases possible. Think about it. Sir, I have another case. What is that? So some student can say that, sir, I have fourth case, that is, see here, B comma C, BC determines B, sir, and BC determines C. So these are all trivial rules, right? Reflexive rules. So they are not important. We don't check them. Okay. Because of that, you don't violate the BCNF condition. So the remaining rules are only B to C, C to B, and B to C, C to B. That's why you will get three structures. One is B to C, second case is C to B, another case is B to C and C to B. So we covered all these cases in everywhere. So left side is becoming automatically super key. From now onwards, you remember, whenever a table contains exactly two attributes, that will be automatically in BCNF. Now we'll come back to BC. So it is already in BCNF because there are only two attributes. Now we'll see this one, ABD. So in ABD, A to B, B to D. We have to see again whether this table is in BCNF or not. First of all, identify left side. Is this a super key? Yes. For ABD attributes, A is a super key because A determines A and B and D. Now B closer. B closer is not ABD, that means B is not a super key. So this is the violation of BCNF. Sir, what to do then? Again, you recursively decompose it into BCNF. Already I told you the procedure. What is that? In this one, see the error. What is the error? B to D is an error. Then create a table again. So I am focusing on this problem. You have ABD. So I am dividing that into two parts. So here error is B comma D, create a table. Now in the old table, ABD, remove BD, you get what? A. But for maintaining anchor, otherwise common attribute, we have to copy B here. So these two will be linked. Sir, how we can link two tables in reality, that means in implementation? Simple. So this B will become key attribute, that's why it will become primary key. See here. So we have a rule B to D, right? Whenever you have B to D, then B is a super key. So we can make this B as primary key in the reality. Just remember it. Because B is determining all the attributes of the table. So such primary key if you have here, then we can make this B as foreign key. So in the real world, we do that. So foreign key refers this primary key so that we can maintain the link between these two tables so that your ABD will become AB and BD. Now similarly here also this B and this B common, right? So make a link like this. This B is a foreign key and here this B you make primary key. So since it is easy to observe that B determines C, that means B determines everything. So that is a key, primary key property, right? So you remember that. Now here AB. Now one surprising thing, AB is a table which is already in BCNF. Why? Whenever your table contains two attributes, that is in BCNF. Two attributes, that is in BCNF. So here two attributes, that is in BCNF. Sir, what if I have three attributes and that table is not in BCNF? Then again you recursively divide. Okay. So let me project the rules first of all. Here, what is the rule we can project? So what were the old rules we had? Forget about these rules. These are all not appropriate. Already they got projected, right? So in ABD, we had A to B and B to D, correct? Remember it. That is our origin or source. Let's begin projecting A to B. It comes here. And B to D, already I projected. Now I projected all the rules, right? Now sir, A to B, B to D, then A to D I try to project. It's not required because whenever you project A to B, B to D, then automatically A to D will be preserved because of the transitive property. So that is the thing. And you have any other indirect rule, check it out. So if you have any other indirect rule, we have to project. So this is about decomposition, which is specially BCNF decomposition, correct? So similarly we can try 3NF decomposition, 2NF decomposition also. If you want to have 2NF decomposition, what you do is only take 2NF errors and do the same. Here I took all BCNF errors, right? So only take 2NF errors and do the same, you get 2NF decomposition. If you want 3NF decomposition, take only 3NF errors and do the same, you get 3NF decomposition. So this is called hierarchical decomposition technique. But the problem is, so sometimes you face two problems with decompositions. Decomposition is good for avoiding the anomalies. You are dividing them into BCNF. But the problem is sometimes this decomposition may not be fruitful. That means it will create two kinds of problems. One is lossless join property, second one dependency preserving property. Every decomposition should satisfy lossless join property, dependency preserving property. What are they? I will explain you. Let's see lossless join property. So let me explain you lossless join property with example. Take this table R, which is actually watchman table. So that contains watchman ID, unique identification number, watchman name and wife name. Forget about the associations, otherwise functional dependencies. Due to your functional dependencies, let's say your table is not in third normal form or BCNF, whatever. So you decompose it into BCNF. So when you decompose this table into BCNF, so let's say you use that hierarchical decomposition technique, then because of that, let's say if you get this kind of association, that means this is your old table and you got now two new tables R1, R2. One is watchman ID, watchman name. Second one, watchman name and wife name. So you might think that, sir, why this kind of division? So don't divide your tables based on watchman name. We have to divide the tables based on watchman ID. You are right. But generally when you have thousands of columns, then it will be very difficult to know whether it is a proper division or not. That's why we are taking one possibility. Let's say that decomposition algorithm you are using, that is going to divide your table into two parts, let's say, otherwise whatever number of parts. So in this example you have two parts. Then if that division happens in this way, where watchman ID, watchman name is one thing, watchman name, wife name is another table, then what I want to say is, this is R1, right? This is R2. Then R1 and R2, if you join, so this is a way we can combine the information. Whenever you have two tables, we use natural join to combine the information. Whenever you combine this information, you should get your old table back, correct? The reason, this was your old table, this was your data, but you divided it into two parts. Then when you combine them, so this is usually the way we combine, right? Natural join. So whenever you combine them using natural join, then it should give what? Your table back. That means your information back. Sometimes what happens, when you apply natural join between these decomposed tables, you might get surprising results. Example, for this problem we will see what happens. So I am applying natural join, then you get your table back, that is 1. So first of all, columns, watchman ID. Since common column is watchman name, it is repeated only one time. Watchman ID, watchman name, wife name. Right? Let's do the natural join. Raju and Raju, it matches, right? So 1 Raju, Raju Rani is nothing but 1 Raju and Rani. Now this Raju matches with this Raju, so 1 Raju, Raju comma Vani, which is actually wrong, right? So 1 Raju Vani. Then you will get 2 Amir, Amir Sanam, so it is 2 Amir and Sanam. Later you get 2 more tuples, 3 Raju, Raju Vani, 3 Raju, Raju Rani. Let me write it. So 3 Raju and Rani and 3 Raju and Raju Vani gives you Vani, right? So now see the data. The old data contains 1 Raju Rani, correct, 2 Amir Sanam, right, 3 Raju Vani. But if you see 3 Raju Rani, which is wrong data, and 1 Raju Vani, which is wrong data, these two are called, spurious tuples. Spurious, otherwise wrong tuples. It's because of your improper decomposition. So this property is called, lossy. That means finally your join become lossy, but I don't want it. Is it the right decomposition? No. If it is right decomposition, you should get your data back, but you are not getting. So this kind of decompositions are called lossy. We should avoid them. So every decomposition should satisfy lossless join property. If you don't have this kind of thing, that means whenever you apply R1 natural join R2, if you get your table back, okay, then we say that property is lossless join property. That means your decomposition satisfies lossless join property. But here one interesting question, given decomposition, let's say someone decomposed the tables. You have a table R that is decomposed into some sub tables R1, R2, R3. Now question is, that decomposition satisfies lossless join property or not? Is it not very important? Yes, definitely important. I never want my decomposition such a way that it is lossy. I never want it. So if I have this kind of decomposition, then you are getting the wrong data. When you get wrong data, what is the purpose of maintaining the databases, right? So that's why the important property of any database is holding the legal data, otherwise right data. So lossless join property is very, very important property we have to hold. Now we will see how to ensure whether otherwise how to check whether given decomposition is lossless or not. So now you try to understand what's the mistake. I mean, what's the mistake here? Taking watchman name which is not unique attribute, otherwise which is not key attribute for either of the tables, at least one of the table, right? So this watchman name, if it is key of at least one table, then you never get this problem. Otherwise, if you divide your tables into two parts such a way that, so that is what my intuition, watchman ID and watchman name, one thing. Second association should be watchman ID comma wife name. If I separate like this, I would not have any problem. We will see such division. What I am doing is watchman ID, watchman name. Second one, instead of this watchman name, I use here watchman ID. If I do that, what happens? It will be 1, 2, 3, right? 1 Rani, 2 Sanam and 3 Vani. If you join them, so 1 matches only with 1, 1. So that 1 Raju, 1 Rani, you get 1 Raju, 1 Rani. Second one, 2 Amir, Sanam you get and 3 Raju, Vani. So you get your data back. So that join will become lossless. From now onwards, you remember one important point. Whenever you divide the tables into two parts, one, the common attribute which you are using here, example here it is watchman ID, right? So if it is watchman ID, then if that common attribute is key attribute, otherwise super key of at least one table, you never get a problem. Remember that fact. Okay. So from now onwards, I use this formula. I apply R1 intersection R2, which is nothing but common attributes. That common attribute should determine table R1 or R2. The meaning of this one I will explain you. So here R1 intersection R2 is nothing but R1 is nothing but attributes of table R1, R2 is attributes of table R2. So R1 intersection R2 is common attributes. What are the common attributes? Watchman ID. This watchman ID should determine all the attributes of table R1, otherwise all the attributes of table R2. So that means that is a property of super key, right? So finally that watchman ID or common attribute should be super key of at least one table of that R1 comma R2. Then automatically your tables will be in lossless. I mean they will become lossless. To understand lossless join property clearly, that means why sometimes your join is lossy, why sometimes it is lossless. So we'll see this example. Let's say you have table R with attributes ABC, and let's say this is the data ABC and DBE. I am taking minimal data, just two tuples. There might be lot of tuples, but just I am focusing on these two tuples. One is ABC, second one DBE. Okay. So when you project this, that means whenever you decompose your table R into R1 comma R2, then this data will be divided, right? So the here A comma B goes and D comma B goes. So that's the idea. Here you have BC attributes, then if I project the data, BC will go here and B will go here, right? Now when you join them using natural join, since B is the common attribute, so what can happen is you get AB BC, that means this B will be linked with this B and this B. That's why you get AB BC ABC, AB BE ABE and DB BC DBC, right? So DB BE DBE. So 4 tuples you get, but actually we have only 2, right? So though you have 2 tuples, why you are getting 4 tuples? The reason is, see, this attribute B is not unique attribute. If really that B attribute is a key attribute or super key, what happens is, that means what I am saying is, so the common attribute B determines every attribute of, let's say, table R2, then B determines C. Really B determines C happens if you maintain that, then you never get this kind of data. That means you never get BC and BE. When you don't get BC and BE, then there is no question of getting spurious tuples. See now, you have, let's say, only BC, not B and something else. So if you have another data with B, let's say that is only BC. Then what happens when you join, you get AB, BC, ABC and DB, BC, DBC and AB, BC, one more ABC if and all if you have 2 BC tuples, right? And you get one more DBC, but you never get spurious tuples, correct? So let's come back again. So when you have data like this now, ABC and DBE, that is not possible first of all. The reason B determines C. So automatically, since B determines C, whenever you have data like ABC, then next DB, since B determines C, this should be C. That is compulsory. That is called functional dependency. Now let's project the data. What you get? Here you get AB and DB. Here you get BC, which is nothing but BC and BC. That's what I'm saying. When you join them, you get ABC, DBC. Of course, multiple ABC, right? ABC and one more ABC. Doesn't matter. When data is repeated, not a issue, right? Same data, right? So we are not creating the new data or we are not creating the new association. But in the previous problem, we created a wrong association. Here, ABC 2 times not a problem. Understand? So I can say that finally the observation is R1 intersection R2, that means common attributes, should be super key for either this table or this table. It's not compulsory to be super key of this table. It can be super key of one of them. So that's why R1 intersection R2 should definitely determine all the attributes of one table. Then for that we write like this: R1 intersection R2 should determine all the attributes of R1. Otherwise, R1 intersection R2 should determine all the attributes of R2. Then you never get this kind of spurious tuples problem. But sir, if you have multiple tables, how to calculate? We will see that later. Before that, I will give one more example. So let's take one example and we'll see whether the decomposition is lossless join or not using this rule. So from now onwards, this can be used as rule, right? So remember it. There is a table and decomposition R1, R2, and the question is whether that decomposition is lossless join or not. Simply apply this formula that R1 intersection R2 should be key attribute, otherwise super key of at least one table. Let's take one example and see that. Let's say R is a table with ABCD that is given, and rules are A to B and let's say BC to D and C to D, something like this. Now your table is divided into 2 parts, R1, R2. We don't know the reason. That algorithm which is dividing the tables, decomposition algorithm, is dividing like this. One is R1 with AB, doesn't matter for us. Second one, let's say BCD. Now the question, such decomposition is lossless or not? For that, simply formula that R1 intersection R2 common attributes should be a key for R1. So need not be a key, otherwise at least it should contain key. That means R1 intersection R2 should be super key of R1 or R2. We'll try that. So first of all, apply R1 intersection R2. What is R1 intersection R2? B. That B attribute should determine R1. That means B should determine all the attributes of R1. What are the attributes of R1? A comma B. That means B should determine AB. Otherwise, B should determine all the attributes of R2. That means BCD. One of them should happen. Where? Either in R1 or R2. We will see that. That's why let me project the rules first of all. So here let me project this rule A to B, then here BC to D and C to D. So once rules are projected, now we'll see that rule. What is that? B should be super key for either table R1 or table R2. Mr. B, are you super key of this table? Then really B is a super key, then B closure will be all the attributes. Let's try. B determines B, but B is not determining A here. That means B is not a super key. So at least B is super key here, B closer. B determines B. B determines anything here? No. B just determines B. That means what? So B is not a super key here. If B is not a super key, then it will have duplicates like hero name. Otherwise, watchman name. Did you remember? So watchman ID, watchman name and wife name problem. In that problem, so watchman name was the common attribute which was not the super key for either tables, like it was neither super key for R1 nor super key for R2. That's why it created a problem, right? So it definitely gives lossy join. Here also B is such kind of attribute because it is not super key of this one or this one. So I say that finally this combination is not lossless, that means lossy. So this is about lossless join property. Now if multiple tables are given, that means in the exam they give you a table R and multiple decomposition. That means they give a decomposition with more than 2 tables. Then how you do it? For that, don't worry, we have an algorithm which is Ullmann algorithm. So we are going to apply that. I will tell you that algorithm. If you use this algorithm, then we can always decide whether the decomposition is lossless or not. It works for 2 also. Of course, for 2 decomposition, that means the decomposition of 2 tables. If you have, we can apply this simple formula R1 intersection R2. But if you have multiple tables in the decomposition, go for this Ullmann algorithm. Let me explain that Ullmann algorithm with example. So this is your table R, A, B, C, D. A determines B, B determines C, C determines D are the rules. And decomposition is R1 AB, R2 BC, R3 CD. Right? So the question is it lossless or lossy? How to do that? So according to Ullmann algorithm, so I'm just giving Ullmann algorithm, but so reasoning is little bit complex. So why this algorithm works and why this algorithm guarantees whether the decomposition is lossless or lossy, how it find out. So it's not really relevant for gate. So especially for gate you should know this algorithm, how it works, that's it. Now we will see how to run this algorithm. In this algorithm, what we have to do is we have to identify number of decomposed tables, 3, right? Then you create 3 rows. Now number of attributes in your original table A, B, C, D. Then create 4 columns. Now we create 2 kinds of entries. One is A, one is B. I will tell you the purpose of A and B. Generally, A will have only one column, otherwise one suffix. So example in this R1, what are the attributes we have? A comma B, right? Then for A and B in this R1 row, we have to write A kind of entries. Okay. Now we have another entry called B entry. So we have to use this B entry for other attributes, like example C and D are not part of R1, right? Here we write B. So usually A will go with only one suffix which is column index AJ, let's say. Now B goes with ith row jth column. That means B will contain row number, column number. A will contain only column number. So here it is first column, right? Then we write A1. This A is in second column, then we write A2. So here it is first row, third column. That's why we write B13. Here it is first row, fourth column. Similarly, for R2, since the attributes in R2 B comma C, right? Then here we write A entries A, but column number 2, column number 3. Now other entries are B's, B and B with column number and row number. So what is the row number? 2 and column number 1. Here it will be row number 2 and column number 4. Next, R3 contains C comma D. Go to Cth position and Dth position and write A. So A3 and A4 column number. 3 third column, fourth column. So here it is Bij, ith row, third row, first column, third row, second column. This is the initialization. Now after that what we have to do is we have to process these rules and we have to change this database. So A to B, B to C, C to D, in any way we can process them, but how to process I will tell you. So whenever you process A to B, what you have to do is you have to observe all the values in the 8th column which agree. Example here A to B. So just try to identify the values which agree, that means which are equal. So no two are equal right here, then leave it, nothing to do. Then go to another rule, B to C. Identify the values on Bth column which agree. So A2, right, they agree. See, this is what I mean A2 and A2 are agreeing, right? So according to B to C property, that means whenever B determines C, when these two values agree, then definitely these C values also should agree. That is a functional dependency rule. Then what we do is, we have to convert one of them to another one. Either I can convert A3 to B13 or B13 to A3. But usually we convert this B entry to A entry. I will tell you the reason. Finally, this algorithm terminates if a row contains all the A entries. That's why our target is seeing all the A entries in a row. For that, whenever you see a B value, when you have an option, you convert it to A. So one reason where we can convert B entry to A entry is here, you see. When A2 values agree, that means see, these two values agree, right? That's why we have to convert B entry to A entry. Now process the next rule, that is C to D. So when you process C to D, so see the entries which are agreeing. So A3, 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 three values are agreeing, right? Then according to C to D functional dependency, if all the D values also should have same value, but here we have B14, B24, A4. So we have to change all of them to one entry. So for that, already I told you that our algorithm's goal is converting all the entries to A's. That's why we convert B24 to A4. Okay. So here also B14 to A4. Now see, all the D values are also agreeing whenever C values are agreeing. Now, sir, how long I have to do this? So this algorithm's termination condition is like this. Either you don't see any entry like modification, stop it, and successful termination is a termination where you see a row with all the A entries. Whenever you see all the entries with A's like this, A1, A2, A3, A4, in not only in this row, any row. So at least one row contains that A's, then we say algorithm is successful. That means your join is lossless. Sometimes what happens, you don't see any modification. That means your algorithm will be terminated because no more updations are possible, but you don't see any row with A's. That is lossy. So we understand this concept with examples so that it will be easy for you to understand. Let me take one more example. Let's see one more example to get more confidence. That is R, A, B, C, D with 5 decomposed tables R1, AD, AB, BE, CDE, AE. So these are the following rules. Now the question, such decomposition is lossless or not? We have Ullmann algorithm, let's apply it. First we initialize this matrix. So how many columns I took? A, B, C, D, E. Each one represents one of the attribute in the table, and this number of rows represents number of decomposed tables. Now these entries, since R1 contains A comma D, mark A and D. Here you have to write A entry, A comma A, and column number. What is the column number here? 1, right? So here column number 2, 3, 4, A4. Now other entries are simply B with 2 indices, row number, column number. For first row, second column. Here first row, fifth column, right? Similarly, we'll fill the other entries R2, A comma B. So here A first column, A second column. Now other things are directly, see, here it is B first row, third column. Here it will be B second row, third column. This is B second row, fourth column, second row, fifth column. Now go to R3, B comma E. Mark B and E where you have to write A entry. A column number, second column. A fifth column. Remaining things are B's. So B third row, first column. Here it is third row, third column. It is third row, fourth column. So on. R4, C, D, E. So C is this one. Here we have to write A entry, A entry, A entry, C, D, E. Third, fourth, fifth. Here it would be B, fourth row, first column, fourth row, second column. R5 contains A comma E, A. Here A1, E, A5. Remaining things are fifth row, second column, fifth row, third column, fifth row, fourth column. That would be the idea. Now what we have to do is, we have to convert all the B entries to A entries using one systematic idea. That is, we have to do that using these rules, A to C, B to C, everything. So the order of these rules can be anything. That means we can use first this one, otherwise this one, anything. So how to use this rule A to C, we'll see now. Whenever you see A to C, mark A and C. Whenever A values agree, C value should agree. That is functional dependency rule. So using that, we are going to convert B entries to A entries. Let's focus. So go to 8th column. We have A1, A1, A1. There are three places where we have A1s, right? That is R1, R2 and R5. Go to the corresponding Cth column. That corresponding entries also should be same, right? That means they should have equal values. A1, A1 and A1, R1, R2, R5. Focus on R1, R2, R5, R1, R2, R5. Here the value should be same. Let's focus on them. B13, B23, B53. What to do then to make them equal? So since all entries are B's, then we have to make all of them to same value. Either you change all of them to B13, otherwise all of them to B23, otherwise all of them to B53. So I choose B13. You can choose B23 also. So B13, here B13. So that is processing of A to C. Now we'll process B to C. When you process B to C, let's mark B comma C. And the rule is whenever B values agree, C value should agree. So whenever B values agree, what are the places B values are agreeing here? A2, A2. Then corresponding values also should agree. But we have B13, B33, right? So we convert this B33 to B30. You can of course use B13 and we can make it to B33, not a problem. Now go to the next rule here, that is C to D. C, so focus on now Cth column. Whenever C values agree, B13, 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 right? B13. So almost all the values are agreeing other than A3. So let's mark corresponding entries here, here and here and here. All that values we should make to same. So one of them is A, right? So remember one thing, whenever one of them is A, other entries also must be converted to A. So that's why one of them is A4, right? Then I make B24 to, let's erase it. So I write here A4, I write here A4, I write here, already it is A4, right? Sorry, we should not touch this one because we are only focusing on B13s. So B13's corresponding entry B54 is A4. Now, when to stop this algorithm is whenever you see a row with all the A entries, we should stop. Otherwise, there is no modification. If there is no modification in the database and no row with all the A entries, then we say algorithm is unsuccessful. That means your join is lossy. There are two things, lossy join, lossless. When can I say that that decomposition is lossless? Whenever really it is lossless join, then you see a row with all the A entries. Otherwise it is lossy. Let's see that. Now so far we processed A to C, B to C, C to D, right? Let's focus on D to C. This time we have to mark D and E, right? So A4, B15, A4, B25, they are not same. A4, A5, it is different. A4, A5, A4, A5. See here, A4, A5, A4, A5, A4, A5. These three rows are same, right? Then go to the corresponding C. In the corresponding C, R3, R4, R5. So this point, this point, this point. A B13, A3, B13. Then one of them is A, right? We have to make other values to A3. So B's should be converted to A's. Then it will become A3. It will become A3. Now, meanwhile, you see any row with A's? No, right? So continue. Then CE to A. So for that, first we should see CE combinations. CE combinations. B13, B15, B13, B25, A3, A5, A3, A5, A3, A5. See, again, these three rows R3, R4, R5 are matching, right? So, whenever that three values matches, then go to the corresponding right side column. What is that? A. Go to R3, R4, R5. One of them is A, right? Then convert other two to A. So, it would become A1. This would become A1. Now, is there any row with all the A entries? Yes, R3, A1, A2, A3, A4, A5. Sir, what if this row doesn't contain all the A's? Still continue. Sir, why to continue? Already I processed A to C, B to C, everything. We should still continue. The reason I will tell you. So, after A to C, you processed all these things, right? When you did all these things, database or this table's content got modified. When tables content got modified, again if you see A to C, you might get different answer, like again you might see some more modifications. Initially when you did A to C, that means using A to C we modified the table, but later you also modified your table with these rules. So then when you go back, because of this different state of the database table, where this A to C might work, and again there might be some more modifications, and so that you can change one row to all the A's. That's why we have to still continue. It's a cycle process entire thing, then go back and process. Then sir, we will be in infinite loop, right? No, you will not be in infinite loop. Why you will not be in infinite loop? I will tell you. So keep on doing. I will tell you when to stop. If you see a row with all the entries, stop it. Otherwise, continue. So example, let's say you started here and you have seen modification. That means there is some modification in the table. Then continue. You have seen modification, continue. You did not see a modification, no problem. See, but you have seen some modification in this entire pass. Then when you go back, so again you have to do A to C because there was a modification after your A to C processing. Then you do it again. This time let's say there is no modification. B to C also there is no modification. So no modification, no modification, no modification, no modification, no modification. You start at one point and you see this entire cycle. In this entire one cycle, if there is no modification because of any of the rules, then if you go back and again if you do, you don't see any modification. That is the point to stop. Let me summarize. So when to stop this algorithm is when in this entire cycle, that means you process a rule number 1, rule number 2, rule number 3, rule number 4, rule number 5. After processing one entire stretch of all the rules, if there is no database modification, that means no modification in this table, then if you go back again and if you see also you don't see any modification, that is the point where we have to stop. Okay. And second thing, if at any time in this algorithm, if you see a row with all the A entries, that is lossless. If you don't see any A entry but algorithm terminated, then it is lossy. Understand? So we'll see one more example so that you can get more confidence about this algorithm. Okay. Now we'll see two more examples to get more confidence about this lossless join property. You have a table R, A, B, C, D. Stop the video and fill these entries on your own. Then cross check with these entries. After that, continue the algorithm. C to D first. So if I apply C to D, so here A3 matches, then we have to convert B24 to A4. Then B to C. So here B column is having A2, then convert one of them to A, right? So that's why it will become A3. Since this is A3, we are converting to A3. Next, A to B. So if you apply A to B here, A1, B21, B31, all are different. When all are different, then we don't do anything, just keep quiet. So far, we processed C to D, there was a modification, and we processed B to C, there was a modification. Later you applied A to B, there was no modification. But should I go back? Yes, you should go back. Before that, is there any row with all the A entries? No. Then we have to continue the process. This time when you apply C to D again, you might see different things. Why? Because first time when you applied C to D, the database was different, the table entries. But next time, this time when you are applying, before that application, so there was a B to C modification. So B to C modified the table. So now you will see the table in a different way. So there might be some changes. So that's why we have to continue. Let me unmark them. So fresh C to D. If you do C to D again, so A3, all are A3. Now see, this was new modification, right? Because of this new modification, now this is going to be changed to A4. So it was not done in the first pass, but now it is done at this moment. That's what I'm saying. So again modification because of C to D. Continue. So, but you don't need to continue. Why? Our goal is stopping the algorithm. Otherwise, our goal is, seeing all the row with A entries. Now we are seeing it, correct? So that's it. So successful. So this is lossless. That's it. You don't require to continue, right? We'll see one more example. So in this example, you have 5 columns. Decomposition contains 4 tables: A, B, B, C, C, D, D, E. Now the rules are A to B, C to B, C to D, E to D. So already I filled these entries. So you stop the video and you also fill these entries. You know how to fill them. Then we'll continue. So A to B. So if you see A to B, so whenever A values agree, no. no A values are agreeing. So don't do anything, just continue C to B. So in C to B, any two C values agree? Yes, A3, A3. Then corresponding value should be equated. So here one of them is A, so other value also we have to make A2, right? So that's it. Next C to D. So C to D, C values here, these two are agreeing, then D values we have to make equal, then it will become A4, right? So there was a modification here and here. I am just remembering them. So E to D. So B15, B25, B35, A5 all are different, nothing to do. If they agree somewhere in some two tuples, we should go to the corresponding D entries and we have to make changes, right? So nothing to change now. Should I continue? Yes, because when first time when you applied A to B, there was no modification, but later this C to B is processed and C to D is processed. Because of these two, there is a change. Because of that change, this time A to B may see some more changes, right? So we'll see that A to B, A1, B21, B31, B41. So there is no change again. So we don't do anything. Now continue C to B. So when you do this time C to B, so B13, A3, A3, B43. So there is a here there are same values A3, A3, but already that modification has been done. Then this time there is no change. Let's remove this modification symbol. Go to C to D. So in this C to D, B13 here A3, A3, but already this modification is done. No new modification I am seeing. Then go to E to D. When I do E to D, same database content you see. So same thing. So no modification. So you made a cycle, this in entire cycle there was no modification, and if you go back again, if you see, then again there will not be any modification. This is the time to stop, but I don't see any row with all the A entries. That's why this is lossy. That's it. This is about lossless joint decompositions and lossy decompositions. Okay.